Hey, happy Saturday morning to you, team. This is your chemistry coach coming at you with video number 11 on our equilibrium series. We only got a couple left. We're almost done with this whole chapter. Pretty cool. Then you can start doing your homeworks. So we have done type 1, type 2, and type 3 equilibrium problems in separate videos prior to this. This will also be a type 3 problem, although you wouldn't know that on a test or a quiz. You got to figure it out first. That's why I always talk about the problem and think about what are we doing? Problem recognition, and then the steps to attack it. Then it doesn't matter what I give you. You just go, oh, been there, done that. That's how you should be on an exam. Been there, done that. Been there, done that. And you just do it, write the stuff down. You know how to approach it. That's the key. All right. So this is going to be a type 3 problem like the last video, but in the last video, we made a simplifying assumption that x was small, and we were able to avoid the quadratic equation and the nasty mathematics. This one, we're not going to be so lucky, so we're going to have to beat our head against an ugly wall and bleed a little bit to do some mathematics. So this is going to take a little bit longer because we're going to have to do the quadratic equation, but there's no way you would know that on a homework problem ahead of time or on a quiz ahead of time, but I want to show you how to think about it. So here's our problem. We've got some antimony, what is that, pentachloride gas, forming some antimony trichloride gas and some diatomic chlorine gas in equilibrium with a Kc value of 0.025. They could have given you a Kp value because they're all gases, but who cares? We can always switch from Kp to Kc. Just go back and check out that video on how to do that. You need the temperature to do that, though. All right. What are the equilibrium concentrations of all species? We've identified our goal. When initially we have 0.112 molar antimony trichloride and 0.0640 molar diatomic chlorine gas. So we're given initial amounts of our two products, nothing of our initial amount on reactant, which we're probably going to make the assumption that it's 0. Otherwise, they would have given us a value. How do we know this is a type 3 problem? One, we're given K, and we're given initial amounts, and we're solving for equilibrium amounts. That's a definition of a type 3 problem, right? We just don't know whether we need to use the quadratic or not. So we got our 4 steps we're going to do. Step 1, we're going to do our reaction quotient Q versus K to see which way this baby's shifting, because we want to know, is it shifting to the right towards equilibrium, right, forming more products, or is it shifting to the left to form more reactants to achieve equilibrium? That's critical because you can't do your ice table properly without that. So that's always step 1. We'll do that here on this board. Step 2, we're going to do our wonderful ice table, which is usually pretty fast. Step 3, we're going to set up our equilibrium expression in terms of x and then solve for x, all right? And hopefully we're going to make a simplifying assumption, and if it's valid, we're good. If it's not valid, we got to do the quadratic. And in the last step, we will calculate all of our equilibrium concentrations. All right, let's do some Q versus K. You ready? Again, you can usually do the reaction quotient in your head. You don't need to write down the mathematics, but let's go through and I'll show you the 2 different ways to think about it. Just kind of thinking about it and then doing it mathematically. So Q, our reaction quotient, is set up exactly like an equilibrium expression. So I'm going to take my products, my concentration of antimony trichloride times the concentration of my chlorine, both raised to the power of 1 because they have coefficients of 1. Sweet! And we're going to divide that by our antimony pentachloride, our reactant, also raised to the power of 1. We love it when everything has a stoichiometric coefficient of 1. Let's plug our values in. So this will be, all right, these are my initial amounts because this is a reaction quotient. If I used my equilibrium amounts, that would be the equilibrium constant. So SbCl3 was initially 0.112 molar. I don't need to put the molarity in there, right? My chlorine was 0.0640. Let's plug our values in. Now remember, we don't really need to do this, and hopefully you can see why before I finish it. We're going to make the assumption that the SbCl5, since nothing was given on it, is 0. So we're going to say that's assumed to be 0, right? Nothing was there, so we're not starting with any. So I'm going to divide this by 0. So if I, as you remember from mathematics classes, if you divide something by 0, you get a slightly large number, like infinity. This is going to be infinity. It's a pretty big number, right? And my kids will ask me a lot of times, what's the biggest number? And I'll go infinity. They go, no, infinity squared. No, infinity, the infinity power. Kids. Okay, anyway, I would make the assumption mathematically that infinity is bigger than our value of k. right? That's actually a fairly big K value, 0.025. A lot of times they're 10 to minus 4, 10 to minus 6. So that's not the smallest Kc value ever, but infinity is pretty big. So I would make the logical conclusion that Q is greater than Kc. We good on that one? And we know if Q is greater than Kc from the prior video, that's going to shift to the left to achieve equilibrium. This is different than the prior problems we've done. All the prior problems we've done, it's shifted right because Q is less than K. We didn't have any products. We had only reactants. Now we flip the tables on you. That's why you got to do step 1. So this is going to be shifting this direction. So in our ice table, these are going to have negative values because they're going down, our products, and our reactants are actually going to have positive values. So let's pause this bad daddy and set up our ice table. All right, team, are you ready? Let's set up our ice table. This is of all the steps, this is my favorite one. I love setting up the ice table because it's big on your page. You feel like you're doing a lot, even though you're not. And it's very simple once you know how you're doing it. So let's set up our ice table. So we're going to put the I, the C, and the E there for initial change in equilibrium, right? Let's set our table up, segregate our little species here. You can make the table as pretty or as ugly as you want. It doesn't matter. So I don't need, I'll leave a little room on the bottom there to do some mathematics. So again, some of you like to write in 9 billion font, some of you are in 0.2 font. Doesn't matter, just big enough so these old eyeballs can read it when I'm grading your tests and quizzes, all right? It doesn't have to be beautiful, just effective. Let's put some information in there. So initially, we made the assumption that we had no antimony pentachloride in there because there was no information provided for us. The antimony trichloride was 0.112 molar. Don't have to stick our units in there. So when we're all done and we get the equilibrium concentrations, we're just going to pop molarity on there because that's what we started with. The chlorine was 0.0640. And all of that was provided for me in the problem. So initial's very easy to do. You just have to make those assumptions. If you're not given anything, we're going to make an assumption on 0. Now the change, again, remember, Q is bigger than K. So this is shifting to the left to get to equilibrium. So my products are going to be negative this time. My reactants will be positive. They all have a coefficient of 1. So I can pick any one of these as my reference point, right? So I'm going to be losing X of the antimony trichloride and losing X of the diatomic chlorine gas because it's shifting away from them, and they both have a coefficient of 1, so they're both losing X. X is the amount that they're going down. On the reactant side, the antimony pentachloride, I'm going to be forming X of that, right? That is the amount that that's going to be produced. So now I can put these together and take the initial amount and add the change that occurs. So 0 plus X will just be X. So at equilibrium, I'm going to have X amount of antimony pentachloride. I'm going to take the initial amount, 0.112 minus X, right? What I started with, subtract how much is lost. That'll be the equilibrium amount of my antimony trichloride. And then the chlorine will be 0.0640 minus X, the initial amount minus how much we lose going towards equilibrium. Great, easy stuff, right? So now let's set up, let's go to step 3. That was step 2. Let's go to step 3. Let's set up our equilibrium expression, make some simplifying assumptions, and solve for X. And then we'll test that assumption. You ready? So I'm going to set up my equilibrium expression. So Kc, which is exactly like the reaction quotient we did earlier, will be the concentration of the products, the SbCl3 and the Cl2, divided by the reactants, SbCl5, all raised to the power of 1. Let's put in our equilibrium values in terms of X. So that the antimony trichloride is 0.112 minus X. The chlorine is 0.0640 minus X. And then the SbCl5 is just X, right? If we just try to beat our head against an ugly wall and bleed all over the place and vomit profusely trying to solve for X, that we could do it, but it wouldn't be very fun because we know what K is. So we could solve for X, but that would require some more advanced mathematics. We're hoping to avoid. Let's make our simplifying assumption. we're going to make the assumption that x is tiny, right? The smaller k is, the more valid that assumption is. Now, k is not super small in this one. It's like 0.025 or something. So let's cross our fingers and hope our assumption's valid. But I'm guessing it's not going to be, because I told you that in the problem in the first place, but you won't know that on a test. So I'm going to assume that the 0.112 for the SbCl3 minus x is just equal to 0.112 because x is really tiny. I'm also going to make the assumption that the 0.0640 minus x for the chlorine gas is just 0.0640 because x is tiny. I cannot do that in the denominator because that's just x. It has to be an initial minus x or plus 2x or minus 3x to make this assumption where the initial is equal to the equilibrium. So I can't make any assumption on the denominator. So I'm going to make the assumption that this is just 0.112 times 0.0640 divided by x. That's my simplifying assumption. So let's solve for x, having done that simplifying assumption, because I know what k is. So let's isolate it for x. So x will be, right, I'm just going to move x over and bring kc down. I'm just going to switch their spots. So that will be the 0.112 times the 0.0640 divided by the value of kc. Just some simple algebra there. Let's plug in our value of kc. So it'll be 0.112, right? That's the equilibrium value of the SbCl3 times 0.0640. That's the equilibrium value of the chlorine gas, making our simplifying assumption that x is small. And kc was, what was it, 0.025? So I've got three significant figures in both of my initial concentrations here, the 0.112, the 0.0640. Remember, a trailing zero with a decimal point's considered significant. The 0.025 is only 2 sig figs. So I'm going to get two significant digits in this. I get 0.2867, so 0.2867, and that will be units of molarity. No need to round that yet. I'm not going to round anything until I actually calculate what was asked for, which are the equilibrium concentrations of all these species. Is this a valid assumption? I don't know. We're going to have to test that assumption validity. All right? And so what we're going to do is we're going to take the value of x divided by the initial amount and then multiply it by 100 and see if that's less than 5%. But there's a little trick to this one because we've got two different things. So we're going to talk about that. So I'm going to erase this, set up a new board, and then we can discuss what's going on. All right, guys, let's do the assumption validity test on this. But there's a little trick to this one. We've actually got 2 times we're assuming x is small, right? We're saying 0.112 minus x is 0.112, and we're assuming 0.0640 minus x is 0.0640. You don't have to do that assumption validity test twice. You just have to pick the one where it's going to create a higher percent error, which will be the one with the lower value, right? So if I make the assumption that x is small here, if I take the value of x divided by the initial amount of chlorine gas, the 0.0640, and times that by 100. If that's less than 5%, that's valid. Then it's certainly valid for the higher value, 0.112. I always test the one that's going to give me the higher percent error, because if it doesn't work for that one, yeah, we're toast, right? So I went ahead and did that. I said, here's my percent error. It's going to be the amount of the change, right, divided by the initial amount of the chlorine gas, because that's the higher value, the lower value, right? So I picked that one. I'm going to calculate that ratio. So I'm going to take x, which is 0.2867 molar, go to 2 sig figs, divided by the initial amount of the chlorine, 0.0640 molar, go to 3 sig figs, times 100. That's an exact number. That converts the fraction into a percent. I get 447.9%. If we rounded that, that'd go to 450%. We don't need to round it. It's pretty, I think, intuitively obvious that 447.9% is bigger than 5%. If we take that value of x, it's going to create massive, massive error. It doesn't even make any sense. How can I take 0.0640 minus 0.2867? That would give me a negative equilibrium concentration of chlorine. That doesn't make any physical sense. So hopefully it's obvious to you we cannot make this assumption. Since that is not a valid assumption, dial 1-800-WHAM-MOMMY, call the wambulance, weep, weep, because we have to do the quadratic equation now. So let's erase this board and refresh our brains, right? If you want to take a second to go back to your algebra course and find the quadratic equation or see if you've got that memorized, write it down before I do. We're going to have to do it. I'm so sorry. All right, you ready for some fun? I wrote all the answers up ahead of time because there's no way I was going to go through this in real time and suck up a half an hour of your day. Let's go through and start back with our original equilibrium expression, right? Products over reactants, raised to the power of the stoichiometric coefficients, equals K, which is 0.025. Plug in the values from our ICE table for the equilibrium. And that's where we were before. We made that simplifying assumption and it didn't work. We had a lot bigger than 5% error. So now what we want to do is get this into the form we need to be able to apply the quadratic equation, which is your ax squared plus bx plus c equals 0. So we need to get the x squared term, the x term, the non-x term, and get that equal to 0. So what I did is I multiplied through by x. So I have the equilibrium constant, 0.025 times x. And then I multiplied through, review your algebra, right? So we're going to get the 0.112 times the 0.0640. That's where this number comes from. We're going to have this x term, 0.0640 times x here, negative, and we're also going to get the 0.112x negative. Add those together, and that's where the 0.176x comes from. And then we're going to have the negative x times the negative x, and that's where the x squared terms comes from. So review your algebra if you need to. You got tons of time now to review all your stuff. No excuses. Put, 50, 60, 70 hours a week into your brain, maybe 10 hours plus into your body while we're under these weird times. Remember to, if you're having trouble studying or whatever, just go take a walk around the block, go shoot some hoops or something like that by yourself, of course. Right? I don't think you could play catch with yourself, but it's kind of weird. Anyway, so then I took this and organized it into the ax squared plus bx plus c form. So I get x squared minus 0.201x plus 0.007168, good to 3 sig figs, equals 0. So A will be 1 in the scenario, B will be negative 0.201, and C will be 0.007168. Again, good, we're tracking our uncertainty to the 3 significant figures there. So if hopefully you remembered your quadratic equation, that was probably drilled into you in algebra. We're going to get 2 values of x. That's why we don't like the quadratic equation so much. X will be negative b, right? Plus or minus the square root of b squared minus 4ac over 2a. That's something I would give you on a test, but I tend not to give quadratic equation problems on an exam. Some of you got the calculators where you just plug it in and solve for it automatically. Anybody can do that. I want you to try to do it this way, the old school way. What if your calculator breaks and then you don't know how to do it, right? Let's plug in a value of negative 0.201 for b. Let's plug in a value of 1 for A and a value of 0.007168 for C. Plug it in, you'll get 2 answers. Do it and see if you get what I get. I get a value of X, my first one, to be 0.15465 molar, good to 3 significant digits. I also get a value of X of 0.046349 molar, good to 3 significant digits there. Because you got the plus or minus term, you're going to get 2 answers. Always one is going to make sense and one won't, all right? So if we look at our initial values, 0.112 and 0.0640, 0.154 doesn't make any sense because we would end up with negative equilibrium concentrations of both of our products, the SbCl3 and the Cl2 gas. So this is impossible, right? This is an impossible value. So I'm just going to cross that out. Boom. That one can't work. But this second value of x, 0.046349, I could subtract that from both of those and still get positive values. So this one's valid. So I'm going to use that as my value of x. Welcome to the quadratic equation. There'll be a couple of those on your homeworks, right? You'll run into them periodically. We've got one more board to do where we're going to now do our last step. We're going to take this value of x, that's a valid, number, plug it into our equilibrium values from the ICE table and solve for the equilibrium concentrations of all of our species. Let's do it. All right. We're on the last leg of our journey, the last lap of the mile, the one that hurts the most in sports but feels the best in academics, right? I'm an old track runner. I ran the 400-meter dash, mile relay, that kind of stuff. Oh my God, that last 100 meters, you're sprinting as hard as you can, was brutal. But I'll tell you, when you're solving a problem and you see the end, you're like, sweet, it's pretty cool. All right, we know the value of X from the quadratic equation was 0.046349 molar, good to 3 significant figures, right? Now let's set up the equilibrium concentrations of all of our species, because that's what was asked for in the original problem. What's the equilibrium concentration of all species? From our ice table, the antimony pentachloride was X. The antimony trichloride was 0.112 molar minus X. And the chlorine gas was 0.0640 molar minus X, the initial minus the amount that was lost. Well, the antimony pentachloride is easy. It's just X. So plug in X and round it, right? So it rounds to 0.0463. It stays there because it doesn't round up because that's less than 5, right? And then I box the rounded value so the person grading your paper doesn't get confused and try to figure out what you mean. For the antimony trichloride, we take the initial amount minus the value of X here. We're doing a subtraction, so we're limited by the largest absolute uncertainty again, i.e. the fewest number of decimal places. There's 3 decimal places here in the original amount. There's 4 decimal places in the value of X, so we're limited to 3 decimal places, which gives us 0.06565 molar. If you round that, it rounds up to 0.066, right? That's bigger than 5. It's going to round that baby up. Now for the chlorine gas, we take the initial amount, 0.0640 molar minus X. This is also a subtraction, so we're limited by fewest decimal places. We've got 4 decimal places in our initial amount, 4 decimal places in our value of X, so our answer will be good to 4 decimal places. We get 0.017651, good to 4 decimals, and since that's 5.1, it's slightly closer to 0.0177 than it is to 0.0176. It's really, really close, right? So it's going to round up to 0.0177 molar. Yes, we are done with this problem. This is about as hard as it gets. I believe we've only got 1 video left to finish up this whole series. Keep up the hard work. You guys rock. I miss you guys.